Hello everyone, and welcome to the first video lecture in our course. I know we started on chapter 23, and I believe we've had at least two lectures on it, but we did not finish it. So what I'm going to be doing is I will review what we have covered in class, and then I will move forward. Uh, so just to let you know that I don't have a lot of experience creating videos. So I have spent the last weekend uh, training myself and downloading the proper software and all of that. And I hope you will bear with me if you find my work a little bit clumsy or a little bit careless. I hope that I will improve as the days goes by. Expect at least one video or maybe two per week where I cover the essential material that we need to cover. Most of those videos are going to be concentrated on solving problems from the textbook, usually the homework problems, and of course talking a little bit about the lesson, covering the lesson itself. So again, we started on chapter 23. I believe, like we said, that we did two lectures on it. So I want to continue on with it, and so let me go to the section. We're gonna section 23.4, and I think we covered that, but I'm going to go over it again. It says the section is sinusoidal wave, and when we say sinusoidal wave, we mean a wave that can be described by a sine or a cosine function, right? And we are covering electromagnetic waves, and these are sinusoidal wave because we can describe them by a sine function or a cosine function. Our textbook chooses the sine function. And then you will have this equation right here, equation 23.3, very important equation. So here you have the electric wave is equal to E max or E naught, which is the amplitude of the wave, right? The height, see where my cursor is? The height of the, this is the red colored one is the electric wave. So the amplitude or the height of the wave is E max, this one. I like to call it E naught. Sine omega t plus or minus kx. Omega here being the angular frequency, and k is called the wave number. Okay, x and t are just space and time. These are variables. So generally, you need to know what is the value of omega and what's the value of k. Okay, same thing goes for the magnetic wave, which is the blue one here, horizontal it looks like. The height of the wave, which is this is the maximum displacement, is B max right there, or B naught, sine omega t plus or minus kx. The plus or minus here indicates that the wave is either moving to the right or to the left. If it's moving to the left, it's plus. If it's moving to the right, it's minus. Okay. And how do you find omega? It's right here. Omega is oops, this is probably the highlighting is not good. There. Omega is equal to 2 pi over tau, or t, the period. Okay. And then the k, or the wave number, is equal to 2 pi over lambda. Okay. All right, so let me show you. Oh, and then the two equations are related by this equation right here, where E is equal to E max is equal to CB. Okay, C being the speed of light, and I think we talked about that in the past. Let me show you an example and show you how that works. The example I want to cover is laser light, and I believe I've done it in class. I'm not sure, but I'm going to do it anyway just for the sake of reviewing it. In this example, it says you have a laser emits a sinusoidal electromagnetic wave that travels in vacuum in the negative x direction. Okay, so let me make a drawing of it. So I'm going to go to, I'm using the software Microsoft OneNote, and I have just learned about it. And I'm going to use my stylus pen. Oh, I'll just start here maybe. So if I make a diagram of this, whoops, what do I do? Oh, click on the pen. There we go. Okay, so here is the x and y axis, x, y, z axis. If I make this to be the z axis, this is x, and this is y right here. Okay, going back to the problem, let me just lift it up a little bit so I can see it right there. He says the laser emits a sinusoidal electromagnetic wave that travels in vacuum in the negative x direction. So here is the x direction. This is the positive x direction right there, right? So the negative is going to be this way. So the wave is traveling in this direction. Oops, it's there we go. And of course, the direction of the wave, we call it s. Okay, pointing vector. But anyway, s. We'll just call it s. Later on, s is also means the intensity of the wave, but that's for later. Anyway, so we have here, this is the minus x direction, is in this direction. Okay. And then he says the wavelength, so the wavelength of this wave is 10.6 micrometer. So let me write it down here. It's a struggle trying to write with this silly pen. Omega is equal to 10.6 micrometer. Okay, and the E field, he said the E field is along the z-axis. So here's the E field. Should I use a different color? That's all right. There it is right there. This is the E field. I'm just, I don't want to use another color because I don't want to mess up my, I'll just leave it black for now. Hopefully I'll do better as the days goes by. Anyway, so here is the E field, and it is equal to, he said, let's read it again. He said the E field along the z-axis with a maximum magnitude of 1.5. So E naught, in this case, the E max, that is, your book calls it max, I like to call it E naught, is equal to 1.5 megavolt per meter, which means times 10 to the 6 volt per meter. Okay, he said find the equation for the E and B as a function of position. So basically, I mean, we know that E is equal to E naught sine omega t plus or minus kx, right? So basically I want to find omega and k. Once I find those, I'm pretty much done. The only one more thing is that I need to determine whether it's plus or minus. Well, what do you think? Should it be plus or minus? Remember we said that if it's plus, the wave is moving to the left. If it's minus, the wave is moving to the right. As you can see from the problem, he said the wave is the s vector, which is the direction of the wave. Okay, s vector means the direction of the wave. It's moving to the negative x direction, which makes it left. So therefore, our equation would look something like that: E equals E naught sine omega t plus kx. Okay, so we're good to go with that. Let me expand this if I can. Oh, it does expand this way, and I can expand it this way. There we go. Okay, back to the book. Do I need the book? Maybe we don't need it. But anyway, if I go back to the previous page, look at this. He said, remember, like I said, we want to find omega and k. Once we get that, we're done with the problem. So omega is 2 pi over tau, and k is 2 pi over lambda. So let me find k first, okay? So we go, how do I do that? Maybe I can use my finger and lift the page. Yeah, I can do that. There we go. You didn't see my finger, did you? Right there. So we have k is equal to 2 pi over lambda, and I given lambda to me, so that's 2 pi, and lambda is, use my finger again, so we got is equal to 10.6 times 10 to the negative 6, and then when we calculate that, you will get 5.9, I'm copying from the book, I have a hard copy beside me here, 5.93 times 10 to the 5th, and the wave number is basically how many waves or how many radians per meter. So the unit of it is radians per meter. Okay. The next step is omega. Now, what is omega? Well, omega is 2 pi f, or 2 pi over tau, the period. Neither of them are given to me, but what's given to me is the lambda, right? So lambda is given to me. Well, we know that the frequency is equal to c over lambda. Okay, so I can find the frequency, I can plug it in here, and then I can find omega. There is another quick way of doing it, and please use you can convince yourself. You just do the derivation to get it. Another shorthand way of getting omega is equal to ck. Okay, so I already gotten k. This is the value of k right here, right? So I can just take that. So therefore it is 3 times 10 to the 8 times k, 5.93 times 10 to the 5th, and then I calculate all of that. And then when I do it, again, I'm copying from the book, 1.78 times 10 to the power of 14 radians per second. That's it, I'm done. So once I got the value of omega, here it is. So now I can find, can I lift it up? Yeah, I guess I can lift it up to infinity. This page doesn't finish. That's cool. So we have E equal to, let me just write it down, E naught sine omega t plus k, as we said it's plus, right? So omega E naught, it's given to us already, and that is 1.5 times 10 to the 6 volt per meter. That's the amplitude, times sine omega is 1.78 times 10 to the 14 t plus k, which is 5.93 times 10 to the 5 x. And there we go. We have an expression for the electric field. So what is an expression for the magnetic field? Well, we know that the magnetic field E is equal to CB, is that right? So, and of course E naught is equal to CB naught, so therefore B naught is basically E naught over C. So E naught, we already got that, so 1.5 times 10 to the 6 divided by 3 times 10 to the 8, and that will give me B, and it's equal to 5 times 10 to the negative 3 Tesla. Okay, and then from there I can get the value or an expression for the B vector. I got everything. So this is the B naught, so all I need is just to plug it in here, and everything else the same. So you will get something like 5 times 10 to the negative 3 sine, and again same stuff. Okay, and there we go. We have that's how we solve this problem. Okay, let me move on to the next topic. The section 5 talks about energy. Okay, and so as you know, I think we talked about it already. Electromagnetic waves carry energy. The evidence for that, you know, when you walk outside, you feel the heat of the sun against your skin. You feel that, right? So that basically because the electromagnetic wave from the sun carries energy, and this energy in the form of, say, heat. And that is, of course, there is energy in the form of infrared and ultraviolet and all other different kind of way. But basically, there is energy there, and we can calculate this energy by this expression. We have what is called the energy density, which is the energy per unit volume, is equal to epsilon naught E squared. More on it in a minute. The formula that I want to concentrate on is this one right here. And that is the average intensity, and I believe we talked about that already. The intensity I, or S average, or S bar, is equal to one of those expressions. Also this expression right here. So you have several expressions to pick. Which one do you pick? Well, it depends on the problem, what's given to you. So you pick the one that fits the problem. They're all equivalent. So you have 1, 2, 3, 4 expression for the energy. Again, you can swap the two symbols. Sometimes it's called S average. I call it S bar, if you remember, or I for intensity. The unit of it is watt per meter squared. Let me give you an example. I think there is an example here that I like. this one. I think this one. Let's do this one. Okay. He says. He said. We will consider an industrial laser cutter that is used for cutting through thin sheets of soft materials. Okay, so we have a laser beam, okay, which gives off a electromagnetic wave with high intensity or high energy. It emits a beam with electric field amplitude. So let's write down what's given to us. Should I go with another page? Yeah, there we go. Let's go here. There we go. Oh, I have to also set up the. Let me just go up. There we go. Right there. I can put a line there. There we go. Okay. So I'm doing here. Let me go back. Maybe I can put this on the side like that, if possible. Something like that. For now. Okay. It says. So what's given to us. This is example 23.4. 20. It's so hard to draw. 23.4. I hope I'll get better soon. Okay, so we have here given to us that E naught is equal to 2.76 times 10 to the power of 5 volt per meter. Okay, this is the intensity of the laser beam. So you have this laser beam over an area big A is equal to 2 millimeters squared. Okay. Find the maximum magnitude of the B field, that's B, and then the energy density and the intensity. Okay. So here's a little picture for you. So here is the area that we're talking about, and then you have the laser beam. Something like that. It's emitted all through the area though, okay? And this is the E naught, and of course with B naught as well. And this is the area here is equal to that, okay? So he said part A, he said find B naught. Well, B naught is just basically E naught over C, correct? So all you need to do is 2.76 times 10 to the 5th divided by 3 times 10 to the 8, and that will give me 9. I'm copying from the book, 9.2 times 10 to the negative 4 Tesla. Okay. Part B, he says the energy. What is it? Find the maximum energy density. So that's U, small letter U, max. I'm going to call it U naught, and that would be equal to C E max E naught squared. Okay, we have everything, so that's just 3 times 10 to the 8 times E naught is 2.76 times 10 to the 5th quantity squared, and then we calculate that, and you will end up with 0.674. And of course, what's the unit of energy density? Is joule per volume, so that makes it joule per meter cubed. Got it? Okay. What else? Now, if he says, if you go back here, he says find the maximum energy density. What if you want to find this maximum? If you want to find an average and you know the max for anything really, basically divide the max by 2. That will give you the average. So if I want to find the energy density average, I like to call it bar, U bar, or U average. That's how your book calls it. Basically, it's U naught, the maximum, over 2. So all you need is take this number and you divide it by 2, like that. And actually, this applies to anything. If you have a maximum value of something, what's the average? Divided by 2. Okay? You see what I'm saying? Okay, so you divide it by 2, and then we will end up getting U max. You know what? I think I made a mistake. The U max here is epsilon. I apologize for that. It's not C. I'm confusing it with B. This should be epsilon naught here. You know, the epsilon, and that's E naught squared. Sorry for the mistake. So this should be epsilon, which is 8.85 times 10 to the negative 12, and we get this answer. Okay, it's epsilon. So anyway, sorry about that. I hope here it is right there. It's epsilon, it's not c. Okay. All right, back to the U average here. So we divide that by 2, and we end up with 0.337 joule per meter cube, same unit. Okay. The next part of the problem, part C, right? He says, find the intensity I. Okay. You can call it I or S bar. Your book calls it S average, whichever you like. And then, like I said, there are different versions. You pick the version that you like. Since we have the average energy and the maximum, if you go back to the previous page, and we go back to the previous page. See this one right here. S average is U average times C. So I'm going to use this one. So S average, S bar is, what is it? I can never remember them. UC or CU. Okay. So it's going to be CU bar. We already got that. So that's going to be 3 times 10 to the 8 times U bar, which is that. And then we calculate that, and we will get an answer of, I'm using the hard copy of the book, I have it in front of me here, and we will get 1.01 times 10 to the 8. And what's the unit on the intensity? Is watt per meter squared. I think I talked about that, why it is watt per meter squared. You remember I told you about how waves propagate. They propagate as spherical waves, and the intensity would be that. Of course, just a little review here very quickly. We're done with this example from lecture last 2 weeks ago. Is that the intensity I is equal to the power divided by the area. Okay, you remember that? So it is big P over A. Okay, so this A can be sometimes the area, the surface area of the sphere, the spherical wave, or it can be the area of like a laser beam, the one day example we just had right here. So this would be the area right here. It's not a sphere or anything like that. So it depends on the nature of the problem. Okay. Okay. Let's go to the next topic, and then we have radiation pressure. Okay. This is probably the last topic before we get into the optics. The radiation pressure, basically what it says is that electromagnetic wave exert force or pressure on an object. You see what I'm saying? So for example, and I believe we talked about the solar sails, and this pressure, whoops, let me go back again. This pressure P, oops, where am I? Oh, I can make the whole thing as a one page. How did I do that? How did that happen? Oh, I click that. Oh, I got a big page here. That's cool. I didn't know that. Okay, so then we have radiation pressure. Okay, and the radiation pressure, again, it's the letter P. Okay, so don't confuse it with this P for power. So this is pressure. Maybe I should just write it as pressure, the whole word. Okay, and this pressure is equal to I over C, the intensity over the speed of light. Okay, now if this radiation, let's say I have a surface here. Here is a surface. Okay, this is the surface. And then let's say I have electromagnetic wave in this direction going on the surface. Let's say from the sun, this is the ground or whatever, okay? So here is the electromagnetic wave, EM waves, okay? Or anything really, laser, ultraviolet, whatever electromagnetic wave you have here, okay? Now, if the surface would totally absorb the pressure, okay, would totally absorb it, and then this, I'm sorry, it would totally absorb the electromagnetic wave, then the pressure, the total pressure on it would be I over C. So the pressure, so for total absorption, absorption, the pressure in this case is going to be I over C. Okay. However, let's say that the surface was a reflective surface, say a mirror or something, or metallic, where it does not absorb anything, it reflects it completely. In other words, let me draw a picture of that. Let's say here is the surface, and then here is the electromagnetic waves on it, right? And as they hit the surface, all of them are reflecting, whatever direction they're reflecting off. So let's say that they're reflecting in this fashion, okay? All of them are reflecting. So what will happen here is the surface. What will happen is that the pressure on the surface is actually twice that, okay? 2I over C. So 2I over C for reflective, and I over C for absorptive or absorption. Okay, you have total absorption, this is total reflection. You got it? So you get that 2. So when you read a problem, ask the question, is it totally absorbed or is it totally reflected? Okay? Of course, the real life, it's somewhere in between, but that would be more advanced topic. Okay? But make sure you understand that. So when you talk about radiation pressure, is it a reflective surface or an absorbing surface? Okay? And this is illustrated with the next example. Here it is right here. And I think I have done this example. I think so, but all right, let's do it. So we have example 23.5. You have a solar sail. Okay. So let's read it together. You have here, he says, in this example, we will investigate the viability of using radiation pressure to propel a spacecraft. Suppose a spacecraft with a mass of, so let's write it down. Let me move this to this side, and then this. Maybe I should put this back. Okay. So let's say that the mass of that spacecraft is given by 2.5 times 10 to the power of 4 kilogram. I'm actually more comfortable now with the pen than before. Anyway, so has a solar sail made of perfectly reflective aluminized kapton. Okay, so remember, look at that word, reflective. What does that mean? If it is reflective, then it is 2. You see what I'm saying? Got it? So here we have kapton film with an area of, so let's see, we have an area of 2.59 times 10 to the power of 6 meters squared. Okay, I'll draw a picture in a second. Let me just put in the data, which is about a square mile, he said. If the spacecraft is launched into the Earth orbit and then deploys a sail at right angle to the sunlight, what is the acceleration? So he's looking for the acceleration, due to the sunlight. At the Earth's distance from the sun, the pressure exerted by sunlight on the absorbing surface. So he gives us the pressure. The pressure is equal to 4.7 times 10 to the power of negative 6 Pascal. Okay, so it is in the proper unit that we had. Okay, now, so how do we do this problem? Let me make it a little bit bigger. move it a little bit up here. So basically what you have here is the solar sail. Think of it like let's turn it into like a square or something just for simplicity. And here is the sun right here, right? And so you get the radiation, the electromagnetic waves on it like that. And then as a result of that, the sail is moving in this direction. That's the direction of motion. And that's the accelerator. It's accelerating, you see what I'm saying? So I want to know what is the acceleration, okay? So he gives us the pressure. Well, we know that when I think of acceleration, I think of force. I know that the force is equal to ma. He gives me the mass right here. And he's asking for the acceleration, right? So I need to find the force. Once I find the force, I know the acceleration. Easy so far. So I asked the question, given from what's given, what is the force? Well, I know that the pressure, P, is force per unit area. I know that, right? So therefore, the pressure, the force, let me erase it. Go this, you pick this one. Oh, there we go, it worked. Back to pen. So in this case, the force is pressure times area. Now I go back to this equation right here. So plug in PA here. So it's going to be P times A equals MA. So therefore A is equal to P times A over M. And guess what? I'm done. It's really that simple. I have everything. So I have here the pressure. Let me lift it up again. It's good that my monitor is interact with my fingers. That's a PC, and on a Mac it doesn't work that way, but that's cool. Anyway, so we have the pressure. Whoops, the pressure is what? Here it is. It is 4.7 times 10 to the negative times 10 to the negative 6. Yes. So we have 4.7 times 10 to the negative 6 times the area given to me as well. Area, there it is right there, 2.59 times 10 to the power of 6. All of that divided by the mass it given to us as well is right there, right here, right? So I have here 2.5 times 10 to the fourth, and then you calculate all of that. It should be a really tiny acceleration. And when you calculate it, I'm just going to get the answer. He did it a little bit slightly different, I guess. But anyway, when you calculate that, you get 9.72 times 10 to the power of negative 4 meter per second squared. In other words, this solar sail will move really slowly, and it will speed up really slowly. It will take it forever to reach certain destination. But again, you're not using fuel. You're just using you're not using fuel from your own. It's not a self-generating. So but that's basically how you work it out. Okay. I'm gonna stop the video here because my next video we're gonna talk about the nature of light, which is section 2.23. Let me go back to the book. I'll make a video, one more video around the middle of the week on the nature of light. Okay, we will cover reflection and refraction and the total internal reflection. We're going to be skipping polarization and dispersion, so you don't need to worry about that, but merely concentrate on reflection and refraction. This is the most important sections, 22.7. I'll make a video on it maybe tomorrow or around the middle of the week. For the time being, please read only up to section up to section 23.5, and then we'll cover the rest of the material. I will cover it for you around the end of around the middle of the week. Okay, and I'm gonna stop the video right now. Goodbye.